And welcome back for a new video on the method of moments and an example to show you how we can use those moments to find mass, velocity, dispersion in a real-life situation. So here I am using an example in an agricultural ditch. You have an illustration here on the top right, and the reason I'm doing this is that because I'm using a one-dimensional model so far, a Gaussian in one dimension, right? And aquifers are always at least in 2 dimensions. So until I do the lectures on dimensions, I'd rather just use a simple example of a ditch. Now, the other reason is a ditch, an agricultural ditch like this, is literally an expression, right? A surface expression of the aquifer, meaning that here on the left and on the right, right, there's water underground that you don't see, of course, the groundwater. But where you have that ditch is literally the level of that, unconfined aquifer that under the field. So really what that water is an expression of, the water table essentially. But again, the advantage is because it's, long, straight, and usually, not very deep and not very wide, we have a nice sort of 1D, right? It's like a line, if you will. So we can kind of understand better our 1D, one-dimensional assumption, and explain that more intuitively before we go into the dimensions. Okay, so our example is a farmer accidentally spills a large amount of a hazardous pesticide into a narrow, long, stagnant drainage ditch, as pictured here. Let's assume the ditch is 2 meters by 0.25, so it's about a half meter squared, cross-section. Again, the cross-section would be here, right? And the whole thing is moving this way. Now the EPA comes and takes some measurements, right, at different position along the ditch, and so they measure, at different position and for the next few days. So again, here is the data concentration through space, and here at different times, right? So this is the first day when they come, and then after 24 hours, after 36 hours, 48, 120. Okay, so this is the data that they find. Use the moments of the concentration distributions to address the questions below. Okay, so first question, plot and label the axis, etc. So this is the plot, this is the actual data, right, that the EPA found in that ditch. There's an Excel file that accompany where you have all the data, and I'll show you the moments in Excel in a second. Okay, so now the question is, what is the mass, right? Oh, excuse me. Observations, I already talked about this, but so the peak concentration obviously decreases with time, right? And we actually know how that decreases because, again, C peak equals mass over square root of 2 pi d square root of time, right? So since time equals right? So it is basically decreasing as a square root of time, which is also a square root of space because, time and space, you can trade by the velocity. So we already know how that decreases over space/time. Okay, the width of the plume increases with time, right? So again, the width of the plume being that variance or standard deviation, you can see that it goes wider and wider and wider, over time because of the dispersion. The center of mass appears to shift, so there is some advection in this case, right? So there is some drifting downstream. Again, remember that we're in a ditch, so there is a bit of velocities. Usually those things are pretty slow and stagnant in the field, but there's still, some velocity, so things move downstream. Otherwise, okay. Right, things move downstream, otherwise they would stay in the same spot, right? So we would have cases like we had before where things look like this. For a strictly diffusive or dispersion equation, they don't move in space. Okay, here we have movement, so there's some advection. And here the area under the curve, so it's not super obvious, but the area under the curve doesn't seem to change much, and we'll verify this, of course, doing calculations, but it doesn't appear that we're losing mass or things are disappearing, so it looks like nothing is really reacting much with the environment. Okay, so how do we calculate the mass? And here is the Excel file, and again, that will be uploaded in your activity. So here's an example. This is the 120-hour data, excuse me. So you have the 120-hour data right here. So again, this corresponds to this data. The area, of course, is 0.5 square meters, we said before, right? So it's 2 meters wide and 25 centimeters deep. So that's a half square meter surface area, or cross section, I should say. So the farmer says, he put in 10 pounds of that pesticide, or he spilled 10 pounds of the pesticide. Now, if we take the 0th moment, again, the mass equals area times the sum of C dx. Okay, so sum Cx dx, that is your 0th moment, right? So if you look at here, the first thing you calculate is dx, right? So we have x. This is your original data. You have C of x, right, at these different places. Now we can calculate dx as simply x minus x, right? So if we look at, let me just clean that up a little bit. So dx here is simply 3. You can see 61 minus 58, right? 61 minus 58, 3 meters. Now 2 meters, 63 minus 61. 0, because that's at the same spot. 2, that's 65 minus 63. So on and so forth, right? So we calculate dx. And then you can calculate c times dx here. So c times dx, so it's literally 0 times 0 equals 0. So this one is 0 times 0, right? This one is 3 times 0.0455, right? So on and so forth. And then you do the sum here at the end. So this is literally equal sum of this column here. And this is your 0th moment, right? So this is sum Cx dx in Excel. Now, one thing that's important is to multiply by the area, right? The reason is, again, dimensions. So the mass is concentration in length per, in mass, concentration in mass per length cubed, typically, right? So you have to multiply this by an area in length squared, so that we end up with mass per length times dx, which is in length, right? So that we finish with just mass, right? So if we sum mass per length cubed times length, we still need to multiply by area so that the units work, okay? So this is the reason. Again, this is really important because especially when we do the dimensions, when we do in 2D and 3D, things get even more complicated. So make sure you track the units. And, essentially what we're saying here is that that mass originally is spread evenly across the area of the stream, right? So it's really m over a that you're calculating, right? The mass is completely, spread around. Okay, so really important to multiply by a so that the units check out and you're actually measuring mass. So when you multiply this number here by a, which is 0.5, right? So 26 times 0.5 is 13.2 kilograms, right? So what we end up with, I'm sorry, this is not very efficient here, but so we end up with, so this is the data for all the pulses, right? For all the measurements, over time. So on average, we find 15 kilograms. For this one, for the 120, we find 13 kilograms. Now, if the farmer said he had 10 pounds in the field, obviously we're quite a bit more, right? We're at least twice as much, right? 10 kilograms is 20-some pounds. So there's more that was spilled. So again, check dimensions, make sure that you multiply by the area when you do this 1D problem. Okay, next question, is this a reactive or conservative pollution? So I already mentioned just by eyeballing that it doesn't seem that the area under the curve, decreases much, but we don't, now we're calculating it. This is literally what the mass is, the area under the curve. And you can see, there's quite a bit of variability, but at the end of the day, it doesn't seem to disappear very much, right? It seems like the mass is somewhat constant. So it's a conservative. It doesn't seem that there's much reaction with this chemical. The diffusion coefficient, so again, D equals sigma squared over 2T, right? So this is, again, this is in MATLAB, right? So the dispersion is, so sigma is given, you know, here, 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 so the standard deviation. So you fit a Gaussian, essentially, you look at what is the standard deviation for this Gaussian over time, and then you do, you know, sigma squared, so standard deviation squared for the variance, divided by 2 times t. You can see that here, these are the times where we measure data, right? And now we have the dispersion coefficient, which is 0.016 squared meters per hour, apparently, according to those calculations. Okay, so now we have the dispersion coefficient, right? So again, if this was an aquifer and we had a bunch of piezometers or, you know, holes in the ground that we could measure concentration over time, you know, we could do that same approach and that same calculation to find the dispersion coefficient. Now here, let me show you, excuse me, here. So the dispersion coefficient we get from this number here. Again, this is just, you know, x times, right, x squared second moment times c times dx. So we do this for each of those lines, then we sum them all, right? This is the sum, and this is our second moment. So the second moment is that big number here, 136,000. Remember that we have to normalize things, right? So second over 0, the first over 0 is here. And then the variance, remember that weird equation that I have right here, right? So second moment divided by 0 minus first divided by 0 squared. Okay, so you have to do all that math in your Excel here to find your dispersion coefficient. Okay, so 0.07 is the result, the dispersion coefficient calculated from the moment for the 120 hour, and then here 0.076, right, is the average, you know, if we calculate it with just fitting a Gaussian to each of those pulses. Point being, the second moment works just fine, right? You can do the second moment, just use the data, calculate the second moment, normalize it properly, find the variance, find the dispersion coefficient. And then finally, how fast is it? So again, this you can get from the first moment. So if I go back to my Excel, sorry, I have to switch back and forth here. The velocity. So again, my velocity is the normalized first moment, right? So the first moment is here, 72 meters. That is the mean distance. And now what we need to do for the velocity is do the distance divided by the time. So that was 120 hours, right? So the velocity is 72 meters divided by 120 hours, right? And that's basically 0.6 meters per hour. Okay, so that's how we get the velocity from the moments. And again, if we go back here, right, the velocity is also just, you know, divide the distance by the time. So here, you know, 72 meters, so same thing, right? You can just read that from the graph. So same thing we found with the moments, but here we just read it and divide it by the time, and you find that velocity is about 0.7 meters per hour. Of course, this is very fast for an aquifer, right? So we're talking about a ditch, so it's, you know, it's not very fast for a river, but it's, you know, an aquifer, again, the order of magnitude of movement is about meters per day, right? So here because we're in the ditch, we're flushing that water, you know, we're flushing that pesticide much faster than we would in an aquifer or in a piezometer. So we'll do examples of that too. Okay, I think this is all I'm going to say about the moments. Again, I'll do activities so you can practice and see, you know, how to use that Excel and those calculations. But again, remember that you can, if you have data of concentration through space, especially, you know, in piezometers, or through time, you know, in a single piezometer over time, you can calculate basically your mass, velocity, and dispersion for your aquifer. All right, thank you.